So hi, welcome everybody to the sixth session of the Isogeny Club. We have today Sabrina Kunzweiler. And today actually she's going to explain to us everything about genus 2 isogeny. So we've had a lot of talks already that dealt with genus 2 and abelian surfaces and a lot of difficult things. But we never actually got into the topic of how you would compute an isogeny or how this works more concretely. So we're very happy that she's here to explain all of this. She's a PhD student at the Ruhr University Bochum. And Sabrina, the floor is yours. You're still muted. I'm not sure if that's deliberate.
No, this was not on purpose. Thanks. Okay, so I hope now everything works out. Perfect. Yeah, thanks a lot for the introduction and also for the invitation to speak here. As you said, I'm going to talk about the genus 2 setting. I think, yeah, recently it has gained a lot of attention. Before this year, I think the focus in genus 2 isogenies was, or at least for cryptographers, was in generalizing protocols based on elliptic curves, isogenies to higher dimensions. And now the SIDH attack has shown that it's even necessary to understand a genus 2 setting in order to evaluate the security of elliptic curve-based protocols. And therefore, the genus 2 has gained a lot of attention, but unfortunately, somehow everything gets quite a bit more complicated if we move to the genus 2. So in this talk, I want to explain a bit with what kind of objects we are dealing here, to explain what a genus 2 curve is, what a Jacobian of such a curve is, and also how to compute isogenies between them. But there, the focus will be on Richelot isogenies, which are the easiest kind of isogenies to compute. Okay, so first, what are genus 2 curves? I think everybody in the audience is very familiar with elliptic curves, but nevertheless, there is a small introduction on the left-hand side of this slide. So very formally, an elliptic curve is a smooth projective curve of genus 1 that has a specified base point. And today, what we're going to look at is at curves of genus 2 that are also smooth and projective, but here one doesn't necessarily have such a base point. The definition that most people will be more familiar with is to say that an elliptic curve is a curve that has an equation of the form y squared equals f of x, where f is some polynomial of degree 3 that is square free. So in other words, the discriminant of the polynomial is non-zero. And such an equation is called a Weierstrass equation. And this also gives us a very nice or a more simpler idea of how genus 2 curves look like. And those can actually also be defined by such a Weierstrass equation. In that case, we have an equation of the form y squared equals f of x, where f is now a polynomial of degree 5 or 6. And also it's square free. And here below, you can see a typical picture of such a hyperelliptic curve. This curve will be the running example in this presentation. So you'll see it on the next few slides as well. So if we talk about hyperelliptic curves or genus 2, maybe I should say, so a hyperelliptic curve is in general a curve of the form y squared equals f of x. And a genus 2 curve is then a hyperelliptic curve where the degree is 5 or 6. So sometimes I'll just say hyperelliptic curve, but in this talk, I think I'll always mean a genus 2 hyperelliptic curve. So now if we talk about such curves, we are usually interested in looking into the points of this curve. And similar as for elliptic curves, the set of points consists of affine points. Those are just the points that u, v that satisfy the equation. So we have that v squared is equal to f of u for those points. And then there are also points at infinity that you can find if you look at the projective closure of the curve equation. And here, if the degree of f is 5, it's very similar to the elliptic curve case. We have just one point at infinity. But if the degree of the polynomial f is 6, there are actually 2 points at infinity. And what also will be important later is to look at the set of k-rational points. So those are the points that have coordinates in the field k, which is our field of definition. Yeah, maybe it's important to note that in the degree 5 model, the point at infinity is always a k-rational point, but in the degree 6 case, the points at infinity might not be k-rational. That's not obvious to see from the description that I just gave here, but yeah, one can, if one looks at the projective equation of the curve, one can see this. Yeah, to make this a little bit more precise, here is again the running example from before, where now I chose as a base field F7, a field with 7 elements. And now to find all the points on this curve, one can just plug in all possible values for the x coordinates and solve for y, if that's possible or not. So, and it turns out that here we find exactly 8 different points on our curve. And yeah, maybe I should already mention the first very important difference to elliptic curves is that the set of points on a curve does not form a group. So that's also why the situation gets more complicated in the genus 2 setting. And before I explain something more about the group structure, let's look at a very specific set of points, and those are the so-called Weierstrass points. Weierstrass points on a genus 2 curve are the points that are fixed by the hyperelliptic involution. So this involution is a map from the curve to itself that sends a point uv to u minus v. So the sign of the y coordinate is flipped. And so this was the description for affine points. For the points at infinity, if we are in a degree 5 model, then the point at infinity is fixed by the hyperelliptic involution. If we are in a degree 6 model, the 2 points at infinity are swapped by this involution. And so now it's easy to see that every genus 2 curve has exactly 6 Weierstrass points. So here you can also see them in those 2 pictures below. On the left, you see a degree 5 model. That's the model from before. There, the Weierstrass points are just, so we have 5 affine Weierstrass points with x coordinates the root of the polynomial f and y coordinates 0, and then 1 point at infinity. And on the other hand, if we have a degree 6 model, there are 6 roots of the polynomial f, but then in contrast to the other case, the point at infinity is not a Weierstrass point. Okay, and here I also wrote down the explicit Weierstrass points for our example. So yeah, that's just the example that I explained here. Yeah, so now if we want to have a group structure on our curve, yeah, to have this, we need to introduce the so-called divisor group. And a divisor in general is just a formal sum of points. So this means if we want to construct some divisor on a curve C, we pick a finite number of points P and write a plus sign in between those points. So this is a formal sum then. And one can also give multiplicities to such points, which here are so by adding coefficients NP. Also, we can just make this more explicit with the example from before. Here I chose a divisor D1. By just choosing 2 points on the curve, 0, 0, and 3, 1. And then I assign multiplicities to this point, 3 to the first one, minus 2 to the second one. And then what we get as 3 times the first point, minus 2 times the second point is a divisor on the curve. And one can also add divisors so if here I define the second divisor with just 1, 0, minus 0, 0. And now the sum of those 2 divisors, D1 and D2, is just defined by summing the coefficients of the points. So here we get the point 1, 0, which is from the second divisor, then 2 times the point 0, 0, which is 3 times at this point, minus 1 times the point, and so on. So like this, we get a group structure. So, and the group of divisors is called the divisor group. An important notion when we talk about divisors is the degree of a divisor. The degree of, and this is just defined as the sum of the coefficients. This means, for example, for our divisor d1, the degree would be 1 because we take 3 minus 2, which is 1. And it turns out that the set of divisors of degree 0 also forms a subgroup of the divisor group. And this will be an important subgroup later. One thing that gets a little bit more complicated when talking about divisors instead of points is the definition of k-rationality. So clearly, if we have a divisor that only has k-rational points in its support, then we say that this divisor is k-rational. But the general definition is a bit weaker than that, because we only need that a divisor is fixed under the action of the absolute Galois group. What this means is that, so here I've given an example on the right of a divisor that is k-rational, although the points are not k-rational. So the divisor d3 has as its point, it's in the support for comma I and for minus I, where I is just the square root of -1. Now the Galois group would send I to minus I, and so it swaps these 2 points in the divisor. This means so somehow the individual points are not fixed under the action of the Galois group, but the divisor as a divisor is fixed, so it's not changed if the Galois group acts on it. So this would be a k-rational divisor, although the points are not k-rational. Okay, and so now finally, before we can say what the Jacobian of a curve is, we have to talk about the equivalence of divisors. So until now, I mean, one could think we are happy because we have a curve and we somehow have a group structure from the divisor group on this curve. But at the moment, this group structure doesn't seem to be very useful, because if we add 2 divisors, we just get somehow a divisor with more points in its support. So what we really want to talk about is about equivalence classes of divisors. And to introduce this, one has to consider divisors that are associated to rational functions. Maybe I just want to explain a little bit more informally what this means. So if we take some rational function, we associate to it the divisor that has in its support the zeros and the poles of this rational function along the curve. So what this means is maybe easier to understand with an example. If we have d1, the divisor that's associated to x minus 3. The function x minus 3 is 0 if x is equal to 3. And so we have 2 points on our curve that have x coordinate 3. So these are the points 3, 1 and 3, 6. And those are both zeros of the function of order 1. So they are in the support of the divisor d1. And then something that's not easy to see from the affine description of our curve, but the function x minus 3 also has a pole at infinity. So we have to subtract -2 times the point at infinity. So this would be now a principal divisor. It's, I think I forgot to say that, but divisors of this form are called principal. And now we say that 2 divisors, d and d prime, in the divisor group are equivalent if they differ by a principal divisor. So for example, if we take the divisor d2 here, that's equivalent to the divisor d3, because the difference of the 2 divisors is just the divisor d1 that we started with, which was a principal divisor. And this group, again, it turns out that if we just look at the set of equivalence classes of divisors, this is also a group, which is called the Picard group. And this is the group that we are interested in when we talk about the Jacobian of a curve. And again, we can also restrict this definition to just having divisors of degree 0, or divisor classes of degree 0, and also to look at only k-rational divisors. And now after this, we can finally say what the Jacobian of a curve is. And it's, again, kind of a formal definition, but what it says is that over any field, so the Jacobian is a variety, and an abelian variety even, which means it has a group structure, and over any field it can be identified with the Picard group. The Picard group was this equivalence group of divisors that we introduced in the last slide. And this definition gives us two ways of looking at elements in the Jacobian. So the first way is to look at elements as equivalence classes of divisors. And in the Genus 2 setting, one can even give a very nice representation of such divisors, and one can show that for each such element in the Jacobian, there exist two unique points on the curve C, so that the element of the Jacobian is represented by P1 plus P2 minus the infinity, where the infinity is just a divisor that has only the points at infinity at its support. So it's either 2 times infinity if the degree of f is 5, or infinity plus plus infinity minus. And so this representation is the one that we will use. And yeah, I think maybe if the description before was quite technical, but maybe what you should remember is that any element of the Jacobian somehow corresponds to a pair of points on the curve. And so this pair are the points P1 and P2. Okay. So on the other hand, there's also a different way to describe elements of the Jacobian. So as I've written here, the Jacobian is a variety. This means it's the zero locus of a set of polynomials in projective space. And for example, there exist different representations of the Jacobian as a variety. And one example is to view it as the zero locus of a set of 72 different quadratic polynomials in the 15-dimensional projective space. And I guess you can already see from this why we prefer to use the representation given above as just a pair of points on the curve, because this description is quite complicated to use in practical applications. Yeah, and as a comparison, for example, so an elliptic curve is also an abelian variety. And as a variety, it can be written, it can be represented as the zero locus of one equation in two-dimensional space. So yeah, it's really getting already, this description is getting quite a lot more complicated if we go up to dimension 2. As I said, we want to focus on the first kind of representation. So we have such 2 points P1 and P2 that are associated with an element R on the Jacobian. And for practical purposes, one usually uses the Mumford presentation of this divisor. So for different reasons, one doesn't always want to use the explicit coordinates of P1 and P2 to represent a divisor when doing computations. And one reason is, for example, k-rationality. So as I said before, a divisor might be k-rational, but this doesn't mean that the points P1 and P2 are k-rational. And so for this representation, one might need to go to a field extension, which is generally something that should be avoided. And so there is a nice representation for such divisors by just using a pair of polynomials, which in this presentation will always be called A and B. So yeah, the description on this slide is a bit simplified. If we just assume that our points P1 and P2 affine points, then the polynomial A is defined as a degree 2 polynomial that has as its roots the x coordinates of the points P1 and P2. And then the polynomial B is just the one that interpolates the points P1 and P2. So we have that B of U1 is V1 and B of U2 is V2. So again, to make this explicit, there is a small example here. I've written down the Mumford presentation, which is given as x squared plus x minus 2, 0 of some element of the Jacobian. And now here we can check how this element looks like in the divisor presentation. To do this, one first finds the roots of A. In this case, these are 1 and minus 2. This means U1 is 1, U2 is minus 2. And then we can compute the y coordinates by just plugging in these x values into the polynomial B. In our case, that's 0, so we get y coordinates 0. Here on the right, you can also see those 2 points lying on the hyperelliptic curve. Okay, so this is the representation that we want to use later if we talk about elements of the Jacobian. Okay, so now after knowing what genus 2 curves are and how elements of the Jacobian can be represented, we can also talk about isogenies of those objects. Again, there is, I want to include a small comparison to the elliptic curve setting. So maybe let's start with that. Yep. So first of all, it's necessary to look at the torsion of an object because isogenies are defined by their kernels, which are subgroups of, on the one hand, an elliptic curve, or today of a Jacobian of a genus 2 curve. And so the first step is to look at the torsion groups. For elliptic curves, the M torsion is isomorphic to the product of 2 cyclic groups of order M. Or in other words, it's a rank 2 Z mod M Z mod U. And if we go to the Jacobian of a genus 2 curve, somehow, we increase the dimension, and this also increases the dimension of, or the rank of this torsion group. And here we actually find that the M torsion is isomorphic to Z mod MZ to the power 4. There's not much of a difference. So for both of these objects, we have a Weil pairing, which is a bilinear alternating pairing going to the roots, mth roots of unity. So in this talk, we'll be mainly interested in talking about Richelot isogenies. And so it's most important for us to study the 2 torsion. This means we consider the case where M is equal to 2. For elliptic curves, if we write down our curve equation as f times as f is equal to x minus ri, or the product of this, so this means that ri are the roots of this polynomial, then the 2 torsion points are just defined like this. So those are the wire, in other words, the 2 torsion points are the Weierstrass points of the elliptic curve. And now if we go to the genus 2 setting, if you remember, elements of the Jacobian now correspond to pairs of points on the curve itself. And so the 2 torsion here just so a 2 torsion element of the Jacobian corresponds to a pair of 2 Weierstrass points. And in the representation, in the Mumford representation, that means that the 2 torsion elements are of the form x minus ri times x minus rj, where this is the A polynomial somehow. And then maybe one other important difference is that if we look at the Weil pairing of two torsion points on the elliptic curve, this will always be -1 if unless the curves are identical. In the genus 2 setting, this is a bit different. There, the Y pairing is -1 if the two torsion elements have a common point in their support. And if they don't have IJ and KL are disjoint sets, then the Y pairing is 1. Okay, so this was it about torsion groups for now, and now we can also say what we mean by isogenies of Jacobians of hyperelliptic curves. So here on the left-hand side, we have again elliptic curves. There, an L-isogeny was an isogeny that has as its kernel a cyclic group of order L. And now, if we look at the genus 2 setting, then isogenies have as their kernel a group of rank 2. So we have a product of 2 cyclic groups of order L as a kernel. And moreover, we need an additional property, and that's that the Y pairing restricts trivially onto this group. So we somehow have to find 2 generators for our group that have trivial Y pairing. If we maybe just briefly go back to the last slide, this means in the 2 torsion setting here that we can, if we want to find 2 torsion points that have trivial Y pairing, what we do is so the first 2 torsion point will be represented by 2 Weierstrass points, and then for the second 2 torsion point, we need to choose 2 different Weierstrass points. If we do that, they have a trivial intersection, and so the Y pairing is 1. Which then means that the Y pairing is also trivial on the whole subgroup. And maybe I also included this condition here on the left for elliptic curves. And that's because that's also a condition there, only that it's trivially satisfied by all groups, because for cyclic groups, the Y pairing will always be trivial. So there's nothing happening there. And maybe another question is how to construct such groups that are maximal isotropic. And if we look first at the elliptic curve situation, the typical procedure is that one chooses a basis for the L torsion, let's say P and Q, and then takes as the group for as the kernel group for the isogeny, the group generated by P plus A times Q for some integer A. And like this, one can generate L different subgroups. In total, as you probably all know, there are L plus 1 different L isogenies, and that's because we missed the group generated by Q in this setting. And yeah, I think so. This procedure is also similar to how you would construct the secrets keys in the SIDH protocol. Now, on the other side, in the genus 2 setting, we can do something similar. We can fix a basis for the L torsion, with the difference that here the L torsion was of rank 4. So we need 4 elements as the generators. And now to construct a maximal isotropic group, one can again just choose now 3 different integers and consider those 2 generators of the group. And one can show that this will always be a maximal isotropic subgroup. With the only condition that I think I forgot to mention, that this basis has to be symplectic. It's again a condition that doesn't appear in the elliptic curve case, because for elliptic curves, we always have symplectic bases for the L torsion, only that we never mention that because it's something that happens automatically. And here in this case, it's something that we need to ask for. if you don't know the term symplectic, it's some condition that comes from the while pairing, and it's maybe similar as looking at orthogonal bases for Euclidean spaces, only that here we don't have an inner product, but instead we have this while pairing with which we can formulate similar properties that we want for our symplectic bases. Okay. I think this was what I wanted to say in general about LL isogenies, and now from now on we will stick to the case where L is equal to 2 and just look at 2 isogenies. And 2 isogenies are also called Richelot isogenies, and they have the advantage that compared to other LL isogenies, they are very easy to represent. And here I've written down the formula. So maybe first, so we have some hyperelliptic curve, y squared equals f of x. And here now I've fixed a quadratic splitting of this polynomial f of x. So f is the product of g1, g2, and g3. And this splitting of the polynomial f actually defines the 2 isogeny that we want to look at. And that has to do with what I explained before, that to find such a maximal isotropic subgroup, one has to consider pairs of Weierstrass points that are pairwise disjoint. And so by fixing such a splitting, we choose the first pair of Weierstrass points as the Weierstrass points that are the roots of the first polynomial, then the second pair will be the ones that correspond to G2, and the third pair, the ones that correspond to G3. And so what we will look now at is the isogeny that has as kernel the first pair of Weierstrass points and the second pair of Weierstrass points. And now what the formulas of Richelot say is that if the delta is non-zero, where delta is defined as here, so it's the determinant of some matrix that has the coefficients of the polynomial gi as the entries. So if this is non-zero, then we end up in the Jacobian of another hyperelliptic curve. And this hyperelliptic curve has a very explicit representation as y squared is equal to, again, the product of 3 different quadratic polynomials, where they are given by this very small compact formula. So here the primes mean that we take the derivative, so as usual. And the isogeny that we get from this is called a Richelot isogeny. So let's again look at the example from before. I think now I increased the size of the field a little bit, just because I wanted to have an isogeny that's a little bit more interesting than it was possible over F7. And we look at the isogeny with the kernel corresponding to x squared minus x and x squared plus 3x plus 2. So this means the polynomial g1 is, it's x squared minus x. G2 will be x squared plus 3x plus 2. And then G3 will be the last factor of the polynomial, and that's x minus 2. So unless I made any mistakes, if you take the product of these 3 polynomials, we'll get the equation from the beginning. So the first step is to compute this delta. That's the determinant of the matrix of coefficients that you have here, which in this case gives us -1. And then in the second step, you compute these 3 polynomials, h1, h2, and h3. So maybe I'll explain the computation of h1. For this, we take, so this is described here. So for h1, we look at the derivative of g2, which is 2 times x plus 3, and multiply it by g3. And then from this, we subtract G3 multiplied, G2 multiplied by the derivative of G3. And what we get is the polynomial H1. And the polynomials h2 and h3 are computed in the same way, just with permuting those indices. Yeah, maybe I forgot to mention this. The indices that are given in this formula here should be viewed modulo 3. Because, of course, yeah, we don't have a polynomial G4 or G5 in our description. So, yeah, that's the definition of Richelot isogenies. And if we were interested in applications like SIDH, this would actually already be enough, because there we only want to know the codomain of our isogenies. But in general, and also, for example, for the SIDH attack, one also wants to be able to push points through the isogeny. So given an element in the Jacobian of C, we want to be able to compute the image point on the Jacobian of C prime. And this is done using the so-called Richelot correspondence. And so the Richelot correspondence is a correspondence on the curve C and C prime that's defined by two equations. And that again only depend on the polynomials gi and hi. To understand what this means, I depicted the situation on the right. So what you have there is, so let's say we want to know which points correspond to the point P, which is the point on the left curve. So maybe I should first say, so this curve here should be our hyperelliptic curve that we start with. And this curve on the right should be the hyperelliptic curve in the codomain. So now we take a point on C and we plug in the coordinates of this point P into this Richelot correspondence on the left. And this will give us so the first equation will then give us a quadratic equation in U prime. And solving this, we get two values for U prime. Now one can plug this into the second equation and we'll get two values for V, depending on U prime, one will always get one value for V prime. And in other words, we have that there are 2 points on the curve C prime that correspond to P. And those are the points P1 and P2 here. So now this somehow explains the correspondence between points on C and C prime. But what we really want is to compute a map between the Jacobians of the curves and not the curves themselves. So if we look at an element of the Jacobian, that's again represented by such a pair of points, P and Q. And what we can do now is we apply this correspondence to each of the points individually. So we compute those points P1 and P2 that correspond to P. And on the other hand, the 2 points Q1 and Q2 that correspond to Q. And this is then a divisor or the equivalence class of this divisor is the image of the point of this element in the Jacobian. The only small problem that we still have here is that we want to represent elements in the Jacobians by just 2 points on the curve. And here at the moment we have 4 different points. So one still has to apply a reduction step, but that's something that's easy to do. There's an algorithm by Cantor to compute this reduction. So given those 4 points, one can easily compute P prime and Q prime on the curve so that this is our image. I think I also prepared an example to go through these steps with our running example. So we consider the curve from before and also the group from before. In this case, the Richelot correspondence just becomes these 2 equations. And now I have chosen a random divisor or a random element of the Jacobian, which has this Mumford representation. And our goal in the example is to compute the image of this element under the Richelot isogeny. And the first step is, so maybe if we go back, here I only explained how to do this if we have this representation. So the first step is to compute those points P and Q in that represent the divisor. So to do this, one would first compute the roots of this polynomial A. And here we find that this polynomial has roots 4 and 8 over F11. So these are the x coordinates, and then you can compute the y coordinates by plugging this into this polynomial here. So what we find is that our divisor R is of the form 4, 4 plus 8, 1 minus 2 times infinity. And now we compute the points P1 and P2 that correspond to P under the Richelot isogeny. And this is done by plugging in the values for P in the correspondence. This gives us on top a polynomial of degree 2, which we can solve for U prime. And then we can plug in the solution in the second part of the correspondence. And similarly, we proceed for Q and get 2 points Q1 and Q2. Yeah, and so this is kind of the standard algorithm to use the Richelot correspondence in order to push points through the isogeny. Okay, so maybe before I continue, I want to ask if there are any questions or something. Okay, then I'll continue by saying a little bit about different methods for the evaluation of the Richelot isogeny. So the standard algorithm that I presented before has some obvious drawbacks. So the first one is, so maybe I should also explain the setting. The setting is that we have such an element of the Jacobian and Mumford presentation, and we want to compute its image in the, here's a prime missing, so this should be J of C prime. And we want to compute its image. And for this one, this requires to compute the roots of the polynomial A. And in general, this might require to pass through a field extension, which is something that one would like to avoid. In particular, because we know that the image has to be defined over the same field as the original element. So it's, in theory, a computation that can be avoided, or a step that can be avoided. But with this standard algorithm that I presented before, it's something that one has to do. And so the first approach to do this is a Gröbner basis approach. And that's also the approach that was used in the SIDH attack for computing the Richelot isogenies. And yeah, that contains quite some algebraic geometry. Maybe to briefly explain how this looks like is one defines an ideal I, which contains somehow all the information that we know about x, y, x prime, and y prime. Where here, now x and y are the coordinates on the curve C, and x prime and y prime are the coordinates on the curve C prime. So what we know about those is that, so we have this Mumford presentation. So for the divisor, we know that x is a root of A, and we also know that y is somehow is equal to b of x. We have the curve equation, and then the other two parts are the equations that come from the Richelot correspondence. And now one does a Gröbner basis computation, and there it's necessary to choose a good term order so that one actually computes a so-called elimination ideal. That's the ideal that only contains those elements that have now as variables only x prime and y prime. So we can somehow eliminate everything in x and y. And in a general case, this ideal is generated by two polynomials. And if one has chosen a good term order for those polynomials, they will exactly be of the form that so the first one, a nu, will be a degree 4 polynomial in x prime. and B nu will be a degree 3 polynomial. And those are the unreduced Mumford presentations for our image. So recall that with the previous approach, we didn't get the reduced presentation of our divisor, but we somehow found 4 different points, P1, P2, Q1, Q2. And so now those 2 polynomials A and B represent exactly this divisor with 4 points in its support. So the last step of this approach would then still be the same as before, that we need to apply such a reduction algorithm. I think the big advantage of this approach is, maybe already obvious from the description, and that's we stay over the field K for all the computations. There's no need to pass to any field extensions to compute factorizations of polynomials or anything. Maybe one could think that Gröbner basis computations tend to be costly sometimes, but actually in the setting that we have here, this is only a very short computation, and it can also be made explicit. For example, there's also a SIDH implementation of the attack, and I believe that in SIDH, the Gröbner basis computations took too much time, so they actually managed to just avoid the computations by doing them in some way by hand or more explicitly. So what's the second idea would be to find explicit formulas. And maybe the general idea is that one can just use the approach 0 that I described in the beginning, the algorithm, but do all the computations over a symbolic ring. So we never plug in concrete values for the GIs, and also not for the coefficients in the Mumford presentation of the divisor, and just perform everything symbolically. For this idea, one also has to take into account the relations that exist among the different coordinates. But if one does that, it's possible to really find explicit formulas. So again, the result will be polynomials A nu and B nu as before. And one can then find formulas for the coefficients of these polynomials. And so these formulas are then just formulas in G0 up to G23 and A1, A0, B1, B0. The problem with such formulas is that they are quite huge. If we don't make any further restrictions, this is actually not, it's in the end not very efficient to use such a representation, and it's faster than just doing, it would be faster to just do the Gröbner basis computations from before. However, one can actually make such an explicit approach work faster. And the idea for that is to restrict to specific curve forms. And for example, what I did, I chose a curve form that is somehow similar to the Montgomery form of elliptic curves, for which the computation of 2 isogenies is kind of nice. And it turns out that for this curve form, also the computation of Richelot isogenies becomes nicer. And for this curve form, one can really find explicit formulas that are relatively short. And this also makes the evaluation of Richelot isogenies faster than the Gröbner basis approach. And then maybe a last approach that can be used is, if you remember from the beginning, that I said we have 2 different ways of representing elements of the Jacobian. There was, the approach that we used the whole time, that for elements, we view elements of the Jacobian as being pairs of points on the curve. And then there was also the representation of the Jacobian as a variety in the 15-dimensional space. While this is computationally maybe not very helpful, there is another variety that one can associate to the Jacobian, and that's the so-called Kummer surface, which is obtained by taking the quotient by the action of multiplication with -1. And if this variety has a representation in the projective space of dimension 3, where it's the zero locus of a quartic equation f, which can also be described very explicitly in terms of the curve equation. So what's the problem with this representation? Well, first of all, by taking this quotient, we lose the group structure. So the Kummer surface is not an abelian variety anymore. But on the other hand, some traces of the group structures will remain if we take such a quotient. And the situation is very similar to looking at X-only arithmetic for elliptic curves, where one could also, somehow by restricting to the x-axis, one can make the arithmetic faster. And what's interesting for us is that the addition of 2 torsion points still makes sense in the Kummer surface. And therefore, it also makes sense to talk about 2 isogenies. So if we have an isogeny phi from the Jacobian of one curve to the Jacobian of another curve, then this also translates to a map on the Kummer surface of these curves. And there's actually a very nice explicit representation of such isogenies on the Kummer surface, for example, in the book by Cassels and Flynn. And maybe I should mention there also exists something called the squared Kummer surface, which is a related object that was, I think, first introduced to speed up multiplication by 2 on Jacobians. But actually what they do was to construct certain 2 isogenies, and in a later work it was used to compute some special kinds of 2 isogenies between hyperelliptic curves. Okay, and so now my idea was to use again the special curve from before. If you paid attention, you will see that it's not exactly the same curve form as before, but it's in some way related. And it's just because it was easier to work with a degree 6 model for the Kummer surface. And then one can actually, using this curve model, one can find very nice formulas for the map on the Kummer surface. And it's even nice enough so that I can write it down on a slide. So what this means is if we have those invariants A, B, C, E for our curve, and we take a point on the Kummer surface. So on the Kummer surface, this was in P3, so any point is represented by 4 coordinates, x0, x1, x2, x3. And if you have such a point as the input, the image under our isogeny will also consist of 4 points, which I called y0, y1, y2, y3. And those can be explicitly represented in terms of those formulas here. Yeah. But unfortunately, I didn't finish the implementation of the whole isogeny chains until this talk. But at least compared to the formulas that I presented in the method before, those are already a lot cleaner than the other ones. So I would expect that this approach should be quite a bit faster than the other one. Okay, so before I end my talk, I also just want to say that especially the beginning of the talk, the introduction about Jacobians and hyperelliptic curves was based on the book by Cassels and Flynn on genus 2 curves, and also by the lecture notes on the arithmetic of hyperelliptic curves by Michael Stoll. And also, if you are interested in more details about these topics, I would recommend those 2 things. Okay, so that's all that I wanted to talk about. Thanks a lot for the attention.
Thank you very much, Sabrina. If there are any questions, you can shout out or write in the chat or Yeah, it was a very nice talk. So you didn't, or you only, like, of course, this talk was about two and two to the end isogenies, but how much worse is the situation for like other primes? Is it?
So for example, so in general, at least one doesn't know about such correspondences as the Richelot correspondence. So the description of such isogenies is more complicated. And I think a general approach is to compute isogenies using theta functions, which is very different to what I presented here. But for example, this comma surface approach also works for 3,3 and 5,5 isogenies, and was done explicitly by, I'm not sure. So for 3,3 isogenies, it was done explicitly by Brun, Flynn, and Testa in a work, and there they also specialized to a specific curve form and deduced formulas for 3,3 isogenies on the comma surface. But compared to the formulas that I have here, there's, I think, I don't know, at some point I counted the number of multiplications, but it's in the thousands or somewhere there. So it's, yeah, or maybe even higher. So already for 3,3, this approach gets a lot more difficult.
Yeah, wow, that's kind of interesting. It's I wonder, like, if you were to do 100, or I guess 101, I'm not sure if that's a prime, but 101 isogeny, then that it's not easy to do.
Yeah, I guess for if you really want to have explicit formulas, it will be very hard. Yeah.
Interesting.
I was wondering about this this while pairing that you presented. That you want the restriction of this to be trivial, but what goes wrong if it's not? Because in the genus 1 case, you always have this, but what do you get in genus 2 if it's non-trivial?
Yeah, that's a good question, and it's something that I didn't really explain in this talk, is that so we're talking about isogenies of abelian varieties, but really what we want is to have isogenies of principally polarized abelian varieties. And this principal polarization, in our case, we get this from having an embedding from the curve into the Jacobian. So yeah, and if we want to consider Jacobian isogenies between Jacobians of curves, we need that this principal polarization, so the embedding that we have from the curve into the Jacobian, gets preserved. And this only gets preserved if the while pairing is trivial. Yeah, so it's something that I didn't really explain, but
yeah, cool.
Nice. Yeah, now I'm totally gonna expose my complete lack of knowledge for genus 2 stuff, but like everybody always only talks about n isogenies, but like what happens if you do something like a 2-3 isogeny or something? Does that even make sense, or is it the same problem? Or
yeah, it's very related to the question from Prime, that yeah, you want to have those isotropic subgroups.
Yeah. Okay. Nice. Okay, yeah, let's thank Sabrina again. And yeah, I think I'll end the recording here.